Hello everyone, you are welcome to clip 3 of part 6, which is related to modern wireless technologies. And now we came to this short range technology named as ultra wideband. So the definition of the ultra wideband is the signal where the bandwidth occupied at least 500 megahertz. So for those signals which occupy this 500 megahertz as a bandwidth, we call them as ultra wideband. There is another definition for ultra wideband where that the bandwidth of the signal is more than 20% of the carrier frequency. For example, if we have signal with carrier frequency of 1 gigahertz and the bandwidth of that signal is 200 megahertz, so even it is less than 500 megahertz, but we call this signal also as an ultra wideband. However, the more famous definition of ultra wideband is that they have bandwidth of at least 500 megahertz. We have two major motivations behind ultra wideband. One has been succeeded in the market and one not yet. We start with the second one, which is not yet in the market, is to achieve very high data rate for short range that it can replace the USB. So it is called sometimes like wireless USB, that it should support up to 480 megabits per second, and according to the requirement that minimum should support 110 megabit per second up to 480 megabit per second. However, due to some problems related to that disagreement between some companies, they didn't come to like one solution or at least compatible solution to support the physical layer. Some companies want to use this multi-band of the ultra wide band, or it is based on OFDM modulation, and others want to use direct sequence ultra wide band, or it is called radio impulses or impulsive solution, and those two solutions were not compatible. So the standard at least was not like successful, so it is failed. uh, but the other motivation for ultra wideband, which was successful and it is already now in market, especially with the modern mobile phones like iPhone 12, iPhone 13, Samsung S21, or Samsung S20 Ultra. So those are already came with chip support this ultra wideband technology, but not for the high speed delivery of information. It can support up to 27 megabit per second, which is not that very high. Of course, it is considerably higher than the Bluetooth, but not very high. So, but the main motivation of using this second of this ultra wideband technology is to achieve high accurate localization and positioning and ranging. So we know from the relation between frequency and time that wider frequency means shorter time. So actually to achieve this 500 megahertz bandwidth, it means that it can be realized with an impulse with a width of 2 nanosecond. So it is very high or very small, like duration of that impulse. So if you generate an impulse with a width of 2 nanosecond, it will occupy a bandwidth of 500 megahertz. So such kind of impulses could be used for ranging. It is like radar, so it works like radar. So you send these impulses, and when these impulses reflected, then you can have very accurate like ranging or localization. So you can use them, for example, for your key tags. So if you have like receiver ultra wideband receiver in your key tag in ultra wideband tag connected you to your, for example, car keys, then you can localize where are they within accuracy of few centimeters, and sometimes the accuracy can be even a fraction of a centimeter. So it is very high accurate technology. It has many applications, like for security, for example, it can replace, or it could replace the keys of your car, or you can open door when you are closing to that door, and so on. So it has many different application, and it is high secured application, or technology. Sorry. Yeah. So, what other technologies available for this ultra wideband? Actually, there is a new standard. It is 802.15 for Z, and this is also for 15 for Z and 15 for A. So this for Z was in 2020, has been issued, and it explains the ultra wideband physical layer, and to reduce the interference to low frequency band. So they have decided to use from 3.1 up to 10 gigahertz bandwidth. Okay, and we have actually mainly three standards or alternatives for the physical layer. It is the impulsive radio, it is called direct sequence, ultra wideband, we have the multi-band of DM, and we have the frequency hopping ultra wideband. But however, that most of the technology available today is based on this impulsive radio or the direct sequence ultra wideband. But again, it is not used mainly for information or delivery, or for transferring of information between devices. Even it can be used with which can support up to 27 megabits per second, but the main application is for localization and positioning. One might ask, what is the main benefits of this technology? Actually, it is expected to have more and more applications for consumers, but also we should remember that it will have huge applications in industry as well. So in different applications in factories, and to track the movement of some objects there, and so on. Yeah. So the impulsive radio, actually, we mentioned this about when we talk about the time hopping code division multiple access. So we saw how to send that impulses or pulses within certain time slots within time frames. So as it is mentioned here, so this is the standard now, that it can be from 3.1 up to 10.6 gigahertz with 14 sub bands. Every sub band is 500 megahertz. Okay. Actually, the ultra wideband, as we mentioned, that can be used for very accurate measure. They use the time of a flight technique of the radio signal in order to localize or find the distance of certain objects. If we compare this ultra wideband standard for localization and positioning, which is included in new mobile phones, with the other technologies, for example, with Bluetooth 5.1, the accuracy is between 1 meter up to 5 meters. So in the average, it is about 2 meters accuracy. And with Wi-Fi technology, the distance can be up to 5 meters, the accuracy. For the GPS, even GPS is not good, is not that applicable indoor, but the error or the accuracy can be within 5 meters. However, this with ultra wideband, as we mentioned, it can be a few centimeters, and sometimes it can be also a fraction of centimeter. And now we come to the another technology. It's called near field communication, NFC. The idea here is that when we need a communication with a very short range, like 5 centimeters or less, for example, then the previous technologies were not suitable. And then we have this near field communication. It has some important applications, like for example, in like to pay, for example, contactless payments, for example. So this in contactless payment or mobile payment is very like important application for this NFC. However, of course, it is very important to have high security here. So the idea, as you can see even from this figure, that we have this cable, it is like antenna around the technology, and actually some it can work over two kind of operation. It can be based on like inductive, it is inductive coupling or capacitive coupling. It is called mutual coupling between the antennas, inductive or capacitive, or it can be also based on electromagnetic connection. However, most of the technology used now, it is similar to RFID, so it uses this inductive coupling. So the NFC actually it operates in a free license band for the electromagnetic. It is at 13.56 megahertz, and the data rate is from 106 kilobit per second up to 424 kilobits per second. It is quite limited, not that high. Okay, and so the inductive coupling is the transfer of energy from one circuit to another due to the mutual inductance induced by the coil antenna in each circuit. So actually, some of the NFC, it can be passive. It means that they don't need battery inside. So and it can take the energy from the reader. So it is called batteryless in that case. Okay. Actually, now we come to the one of the important topics for low range communication is low energy communication. So it is very important to have very low energy consumption for many applications, especially when we talk about Internet of Things. One of the applications of the Internet of Things that it can be in a remote area, or in some areas where it is not possible to reach, or it is not cost effective to replace or recharge batteries. Um, One example, if you distribute hundreds or thousands of sensors with included some wireless communication capabilities, and they have been spread within a remote area to track some physical quantities like pollution, for example, or temperature or smoke, or track some objects there. So in that case, it is not reasonable that you can send someone from time to time to change the batteries for those hundreds of sensors. So those sensors actually are disposal sensors. It means that they can work as far as they have energy, and after that you can just ignore them. So those sensors usually they are small size, and they are equipped with coin type battery, and they should work for months or years. Some of them they should work up to from 5 to 10 years, like without replacing the battery. Of course they can work at very low, like active cycle. Some of them they send packets like once for a few seconds per day, but anyhow they should work for years. So in that sense, the very low energy is very very important in many of those applications. So this is the reason that it takes special attention in communication research, how to achieve this low energy communication. Also in your like smartwatch, you want it to work for like a couple of weeks before you recharge them. So they are like quite annoying that you need to charge your like watch every day, for example. Part of this low energy communication is included in the standard. For example, the low energy Bluetooth BLE. It has started a few years ago. started with Bluetooth version 4.1 and so on. And also we have new standards for other technologies as well, like ultra wideband also. They try to minimize it is energy consumption, so that we have already tags with based on ultra wideband with coin type battery, and they promise that it can work for up to 7 years without the requirement to change their batteries. The energy consumption in IoT device is due to three possible reasons. One is the radio part, mainly during the transmission phase. Second is in the network part. For example, to explore devices, to send hello signal, and for retransmission, for communication protocols to achieve this communication between devices, and also the application part, which is also information processing and operation inside the device. For example, when you sense the temperature, or you sense, or the device senses the pollution, they will need to process this data. So this processing of data will consume energy. And of course, also the network part, for example, retransmission or communication protocols, also they use the radio part. However, that I separate them here because we need, in the research, we might concentrate on the radio part, for example, using multiple antennas, what kind of frequency, what kind of carrier modulation technique. In the network part, how to modify and develop the MAC layer in order to reduce the consumed energy. There is one thing here related to the distance between of the transmission distance. To make it clear, in wireless communication, we have very high attenuation or very high losses. So if we assume, to take this example to clarify this point, if we want to receive power equal to zero point 0.1 microwatts, so what 0.1 microwatts is the required receiving power. So for the distance between the transmitter and receiver, once it was 10 meter and 100 meter and 1000 meter. So we want to compute what is the required transmitting power in order to achieve such kind of receiving power. Of course, the receiving power is very important because the signal to noise ratio at the receiver should be more than certain value in order to have successful communication, or for the receiver to be able to decode the signal. Okay, so now we use the channel model given in part 1. So that this is the channel model in part 1. It is called two rays model. And they said here in this example that assume every value is 1, so just normalized value, and now we need to compute the transmitting power. Okay, so it means that the receiving power equal to transmitting power divided by the distance of the power 4, which means that the transmitting power equal to the power received, the required power received times distance of the power 4. So the required received power is only 0.1 microwatt. And then in case that the distance is 10 meter, so it becomes 10 of the power 4, and means that the required transmitting power is only 1 milliwatt. So 1 milliwatt is enough to achieve 1.1 microwatt at the receiver if the distance between them is only 10 meter. Okay, what happens if the distance is 100 meters, so 10 times more? The power will not multiply by 4, but by 10. But actually the power, you can see that this is the required receiving power times 100 of the power 4, and we can see that the required power now is 10 watt. It means that the required transmitting power is 10,000 times the required transmitting power in case of 10 meters. And in case of 1000 meter, the required power will be 10,000 more, so which means that 100,000 watt, 100 kilowatt needed to deliver the message for 1000 meter, but it was only 1 milliwatt if you want to transmit the message for 10 meters. Okay, so because of that, we found that the multi-hop communication might solve the distance problem. So by using this multi-hop, if we want to transmit the signal from terminal 1 to terminal n, of course not necessary to be the same distance between them, but the idea that by using multi-hops we can deliver the message for longer distance without using very huge transmitting power. Of course, it has also some disadvantages as we will see them later. So here, in case that you want to send the message for 100 meters in the previous example, then you need to use 10 times multi-hop, if assuming that every device is only 10 meters apart. So in that case, the total required power, because for every transmission for 10 meter is 1 milliwatt, as we saw from the previous example, and then for 10 devices we will need 10 milliwatts total. However, that it was 10 watt needed if we want to transmit the message in one hop, in just in one time. So we can save on the total power 1000 times less. So this is the multi-hop is very essential in IoT applications, in social networks, especially in mesh like topology. Of course, it has problems. For example, it will induce more delay, because if you want to transmit from the transmitter to the receiver in one hop, it is faster, but now you need to send from terminal to terminal, from terminal to terminal, and so on. So in that case, if this terminal, for example, was busy, then the transmitting terminal should wait until this becomes free, and if this is busy, then this also have to wait until this becomes free, and so on. And in every transmission there will be some like processing, so the time delay can be very large. Also, we have problem that if we have in the middle one of the essential sensors was dead due to any reason, maybe battery or malfunction or whatever, or any fault, then the connection can be like disconnected. So it will not be possible to connect from the transmitter up to the receiver. Of course, in that case, we need to increase the redundancy of the network so they can find some other path up to the receiver. Okay, so we have also problems for this multi-hop, but sometimes it can be the only solution available. For example, if you have multimeter readings, so instead of installing long distance modem in every meter, for example, in one building, so in that building maybe there is 100 for example, we have 10 floors, and in each floor maybe we have like 4 buildings, so we have 40 buildings, so we have 40 meters there. So the meters, they can connect to each other by using multi-hop. Okay, and we then finally we have one data concentrator that they collect the whole data through this one, and then we use, for example, cellular network to transmit the information. So the multi-hop communication can be useful for many different applications. Low energy communication, as we mentioned, that this is in the transmission, but also in MAC protocol, that we should use that some protocols which enforce the device to go to sleep when there is no transmission. So we don't need to have that everything awake inside the device, inside the device. So there's a control that it goes that to sleep to save energy. However, sometimes we need to keep the receiver like awake in order to receive like a signal. So when we receive signal, then we need to make the whole device to be on again. So we have actually many smart technologies in order to make this sleep and sleeping algorithms for the devices. There is another technology which is Relatively it is new, even the concept is very old, but now with this advancement in technologies that it becomes alive again, which is batteryless communication. The batteryless communication, as we mentioned, it can be based on that getting the energy from due to that inductive coupling, and it is similar to like charging your mobile phone, contactless charging of your mobile phone. So the delivery of the energy is by the inductance. So there is inductive, or there's coil in the charger, and there's also coil above the battery of your mobile phone, where there will be some contact due to the inductive or induction between the two coils. However, there is another interesting method or interesting way to get energy. We know that we have man-made signals everywhere. So, for example, in this room or around you, there is many signals coming from like your TV channel, AM signal, FM signal. We have a lot of electromagnetic waves around us, and also Wi-Fi signals, for example, cellular network signals. So the idea why we don't harvest this electromagnetic wave and convert them to energy, and then we use this energy to transmit our information. So it is like harvesting than transmitting. So harvest energy, just use some antenna, collect this energy, receive it. It is very small. It is in terms of a point like zero 0.01 or zero point 0.1 microwatt, and it can be much smaller even. So however, that if we just have some like smart harvesting circuit, that all the time, because the electromagnetic wave is free, it is available, so just harvest this one, have some battery, and try to store as much as you can, and maybe within 24 hours of harvesting you will have enough energy to send a few packets for a few meters. So this is called batteryless communication. It can be useful for like in a remote area, and also for batteryless application. So especially if you want to transmit this signal for only few meters. Okay, and then we will have devices without any batteries, and still they can be useful for some application. So this is the idea. Actually, you can see that we have like 4G network, we have FM, we have TV. So those signals that we this is RF like powered device. So we just harvest or collect this energy. Okay, and then we can, once we have enough energy, we can use them to deliver a message to another device, like routing. And this device, maybe when it collect enough energy, they can deliver this message to the router or gateway, and the gateway of course they can send them. There is also another technology, is that the gateway, which is battery based, they can communicate with the device, and then they send them message, and base it of this communication, this RF powered device will take the power from the RF signal, and then they can use this signal to reply to the receiver. However, that the working range can be only maybe fraction of 1 meter. It can be less than 1 meter. So it has some special kind of applications. Yeah. So it is called, as I said, RF energy harvesting network. And this is for the simultaneous wireless information and power transfer, is called SWIFT. So the same transmitter, which is power battery based, they send electromagnetic wave, strong electromagnetic wave, which contains information to the receiver. The receiver takes the information and takes also energy from this electromagnetic wave, and store the energy, and then they can answer back, or respond to the transmitter with some required information. It is a little bit different than the inductive based. So this NFC or this RFID is based on the induction. So the transmitter doesn't transmit electromagnetic wave, but just you close the coil, which makes inductive coupling between the transmitter and the receiver. So the technology is slightly different and conceptually different, but it is quite similar, that the operation itself is quite similar. Okay, that's enough about short range communication technology. And now we come to the medium range communication technology, and it is actually based on the very, very successful technology known as the Wi Fi, or the IEEE 802.11. So, this is the very famous standard, and it is considered as one of the most successful local area network technologies, and actually one of the most successful wireless communication for the computers. It is enough to mention here about 3 billion Wi-Fi enabled devices are shipped globally each year. Okay, so actually IEEE 802 refers to the standard issued by IEEE organization regarding computer networking. So whether it is wireline or wireless, we call them 802. This is the standard number. The standard number 802.11 is related for the wireless medium range communication. Wireless medium range communication. Medium range means that it is a few hundred meters in under special conditions, but in general it is for one floor building. It should be able to cover one floor building, but actually it can cover more. Okay, and the multiple access of this standard is based on the carrier sense multiple access with collision avoidance that we explained before. Actually, it has many applications. The simplest application is just to connect it to your computer or your mobile phone, but it has also many other applications, as we will see. There are many different versions of IEEE 802.11x. So we put here X, where X can be A, B, J, N, AH, AC, AX, and so on. So we have different standards for this A02.11. So the main difference between all these is in the physical layer, not in the MAC layer. The major difference is in the physical layers. So to achieve higher quality of service. All these standards, they use the ISM bands, so it is unlicensed band, and it is mainly for 2.4 gigahertz, and also they use the 5 gigahertz, and in new versions they start to use also the 6 gigahertz bandwidth. Um, so even a new standard or the new frequency management or bandwidth management starts also on the 5 gigahertz. Okay, if we start with the oldest 802.11, which is RA and B. So actually the 11A, it was working at 2.4 gigahertz. Actually it was working at 5 gigahertz, not 2.4, because actually they want to avoid using this 2.4 gigahertz, 2.4 gigahertz, because it was very like crowded. However, that 802.11b was working at 2.4 gigahertz. So even a standard came before B, but B was like split more than A in the beginning. So because at that time when they came the standard, it was easier to like manufacture and distribute these frequencies at 2.4. So the modulation method is based on OFDM and 52 subcarrier. Actually 48 subcarrier used for data and 4 for pilot. We have also the subcarrier separation is at 0.3125 megahertz, which means that for the 52 subcarrier we will have 16.25 megahertz. However, that the total bandwidth per channel is 20 megahertz. So it supports different data rate depending on the channel quality from 54 up to 6 megahertz. So it depends on the channel quality. It has adaptive like a scheme. So if the channel quality is very good, that it can submit up to 54 megabit per second. Sorry, up to 54 megabit per second. And if the channel quality is low, then the bit rate can be down at up to 6 megabits per second. So the modulation quality, actually they are different for depends on the channel quality between binary phase shift keying up to 64 QAM. And then we have 802.11b, where it uses 2.4 gigahertz bands or carrier, and the data rate supports up to 11 megabits per second. But however, that the maximum throughput is 5.5 megabits per second. It uses also carrier sense multiple access with collision avoidance, and it is not OFDM based, but it is direct sequence spectrum based. So also it supports adaptive data rate based on the channel equality. Then we have 802.11g, and in this is also using OFDM but at 2.4 gigahertz, and also it supports up to 54 megabits per second. Actually, it is almost identical with 802.11a, but the only difference is in the frequency. So they use the band at around 2.4 gigahertz instead of 5 gigahertz. And we have 11AH, where actually it uses lower frequency, carrier frequency, around 900 megahertz, to cover larger range, so it can support more than 1 kilometers. So it is in that sense, it is not really local area network, but it's about wider range, and mainly it is used mainly for reading smart meters, collecting data. So it could be used with IoT applications. The data rate is around 100 kilobits per second, so it is not that suitable for internet, for application like downloading data or files, uploading files, and so on. So it is much lower speed. Then we have actually the 802.11n, which is known as Wi-Fi 4, and version 4, or generation, or fourth generation of Wi-Fi. And in that standard, actually it can support up to 600 megabits per second. It uses also OFDM, and they increase the data rate by duplicating the channel bandwidth. So we know that in the previous standard, the bandwidth was 20 megahertz per channel. Now it has been increased to 40 megahertz, and also they use better and higher coding rate. They reduce the guard time between symbols. They use higher number of subcarriers, and actually they introduced in this generation to use the MIMO with 4x4 antennas. And after that, we have the fifth generation of Wi-Fi, which comes with 802.11 AC. So it can support up to 1.8 gigabits per second, at least theoretically. And the huge improvement is due to the increasing of the bandwidth from 40 to 80 and even 160 megahertz in the 5 gigahertz band. And also they use higher number of antenna, MIMO antenna. Now it is 8 by 8. And also they increase the modulation level up to 256 QAM instead of 64 QAM used in 802.11n. You know that 64 QAM means that you send 6 bits per symbol. Here you send actually 9 bits per symbol. Yeah, because 8 is 128, so it is 9 bits per symbol. So you increase considerably, you increase the bit rate. Okay. And then we have the sixth generation of Wi-Fi, which is known as AX, We have also enhanced the sixth generation. So in that band, we increase the bands that we try to use. Every unlicensed band is from 1 giga up to 7.1 to 5 gigahertz, so including the 2.4, 5 gigahertz, and also the 6 gigahertz. 802.11ax, they use some of the technologies applied in the fourth and fifth generation, like of DMA, using power control methods to reduce interference, and also they can support up to 1024, which means that 10 bits per symbol, that, and using MIMO, multi-user MIMO, and they use that channel width up to 160 megahertz, and theoretically the data rate, it can be support up to 9.6 gigabits per second. And finally, we have this Wi-Fi version or generation 7, and it is expected to come to the market in 2024. And in this version, they use most of the bands in 2.4, 5, and 6 gigahertz, and also they use 4064 QAM, 4 key QAM. And it is mentioned here that this modulation level is the first time to be used in wireless communication. It is very high number of bits per per symbol, and also it utilizes 320 megahertz bandwidth, which means that it can support up to 46 gigabits per second. It is huge. It is really huge bit rate. Yeah. So this is the seventh generation that it is expected to come within like 2 years. Yeah. So actually now we have seen those the main standards of this Wi-Fi, which is used for the local area network, and it has also many applications in industry and in like um, governmental application, like in factories. So it can be used actually not only for the like consumer communication, but it can also collect data from sensors in IoT. For example, if you have distributed IoT in one factory or at home, then Wi-Fi can also collect the data from these Wi-Fi IoT devices. If the distance is not that a large distance, then this Wi-Fi can also deliver energy to those batteryless IoT, and those batteryless IoT, they can like harvesting this energy from this electromagnetic wave or from other sources like temperature and so on, and collecting energy. And once they got enough energy, then they can transmit their data when it is available. And those are very useful in case that we don't need like continuous transmission. Some sensors, they need to transmit like once a day, for example. For example, if you have sensor like buried in building, which measure the humidity, for example, maybe once every couple of days. So in that way, it is reasonable that we harvesting energy every couple of days. We have enough energy to transmit a few packets to inform the monitoring device or the control room about the humidity inside that building or inside that concrete and so on. So actually we have many applications. We will see more applications when we come to the part related to the IoT and their applications. Thank you very much. And then we come to the part 7 about the cellular technologies. Thanks a lot.